This is section 2.2 in Math 1114. It's about matrix multiplication. This section is going to require a little bit more work than the previous section, section 2.1, which was addition. Matrix multiplication, you need to practice that a bit to kind of get down the process. Let's take a look. Section 2.2, matrix multiplication. We begin with the definition of matrix multiplication. Let A be little a sub ij, let that be an m by n matrix. In other words, it has m rows and n columns. And let B, which is little b sub ij, be an r by s matrix. So it is r rows and s columns. If n is equal to r, in other words, if the number of columns in A is equal to the number of rows in B, then AB is an m by s matrix whose ijth entry, you remember ijth means the entry in row I, column j, that is equal to little a sub I1, little b sub 1j, plus little a sub I2, little b sub 2j, plus, etc., plus little a sub in, little b sub nj. Now that looks pretty crazy. So let's see if we can tell where this comes from. Let's take this equation and try to analyze what it's trying to say. First of all, we look at our A matrix. Our A matrix was made up of little a's. The ith row, row I in other words, is made up of little a sub I1, little a sub I2, etc., up to little a sub in. That was row I in matrix A. The J column in matrix B, I haven't shown you all of matrix A or all of matrix B, but the J column in matrix B is made up of little b sub 1j, little b sub 2j, all the way down to little b sub nj. Multiplying row I in A by column j in B is going to give us the ijth element in AB. As you see, if we take the entry in the first row, in the ith row of A, the first entry in the ith row of A, by the first entry in the jth column of B, we get little a sub I1, little b sub 1j. Next, if we match up the second entry in row I of A by the second entry in column j of B, we get that next entry in that equation above. Little a sub I2, little b sub 2j. Last, if we take the last entry in row I of A and the last entry in column j of B, we get the last entry in the ijth element of AB. So we essentially match up all of the elements in row I with all the elements in column j of B, and that gives us the ijth element of the product. We had said all this would work if n was equal to r. If n is not equal to r, AB is not defined. We're not allowed to multiply two matrices that don't have those inner elements corresponding, or those inner dimensions corresponding. Here's what I mean by that. If we have A, which is an m by n matrix, and B, which is an r by s matrix, n and r have to be the same values. Then the product AB would be m by s, the outer two dimensions. So the inner two have to match. The outer two give you the size of the product. Let's take a look at an example. If I have the matrix 1, 2, 3, 4, which is a 2 by 2 matrix, times the matrix 1, 0, negative 2 in the first row, negative 4, negative 1, 7 in the second row, which is a 2 by 3 matrix, the answer to that, the product, AB, would be a 2 by 3 matrix, the outer two dimensions, the 2 and the 3. So let's look at this example. I know I'm going to get a 2 by 3 matrix. Here's how it works. The entry in the 1, 1 position I use row 1 and column 1. Row 1 in the first matrix is 1, 2. Column 1 in the second matrix is 1, negative 4. So as you see, I have in the 1, 1 position 1 times 1 plus 2 times negative 4. As we go across, next you'll see that I have 1 times 0 plus 2 times negative 1. That is the first row, which was 1, 2 in the first matrix, by the second column in the second matrix, 0, negative 1. You can pick any entry. For example, if I picked the entry in the third row, excuse me, not third row, but second row, third column. Second row, third column would use the second row of the first matrix, which is 3, 4, by the third column in the second matrix, which is negative 2, 7. So I would multiply the 3 times negative 2, the 4 times 7. So any entry in the product matrix, we figure out how to get it by using its position. So if something's in, say, first row, second column, I use first row, second column of the two matrices I'm working with. Here as my result, I got negative 7, negative 2, 12 in the first, negative 13, negative 4, 22 in the second row. You'll often see a lot of examples that don't even have the matrices named. They may just say, hey, A is a 2 by 3 matrix and B is a 3 by 2 matrix. What size is AB? AB is going to be a 2 by 2 in that case. You use the outer two dimensions. So if I have A first and B second, the outer two dimensions would be 2 and 2. Could I multiply B times A? Yes, I could multiply B times A. In that case, B would be first, it would be a 3 by 2, and then A, which is a 2 by 3. The outer two dimensions there are 3 and 3, so BA is a 3 by 3 matrix. There's also some properties in this section. If R is a scalar, in other words, it's just a constant, and A is an M by N matrix, and B is an N by P matrix, and C is a P by Q matrix, I have this associative property of multiplication. It allows me to multiply A times B first and then times C, or I can multiply B times C and then times A. I also have this associative property of multiplication, where a real number, R, is involved. I can multiply A times B and then by R, or I could group the R with the A, or I could group the R with the B. That little constant R can slide around to be with A or to be with B. It can kind of slide around anywhere it wants to go, pretty much. Some more properties. We have a distributive property. If C is over on the right, if I'm supposed to add A and B first, and C is over on the right that I'm supposed to multiply by, I could instead distribute C so that I would have AC plus AB. Now there's one small problem with that. That is the distributive property. There's one small problem with that, and that is, are these things defined? Am I able to add A and B? I said that A was M by N and B was N by P. Well, M by N and N by P have to be the same thing in order to be able to add those together. So you need to watch that. You also need to watch whether or not A times C is going to be defined. I set it up so that B times C would definitely be defined, but you need to make sure A times C is also defined. So all of these properties, really, you have to make sure that the sums and the products are defined before you can say that the property exists. Again, I have a distributive property. If A is on the left, I can distribute A to B and C. And again, we need to make sure B plus C is defined and that A times B is defined. Well, I set it up that A times B would be defined, but that A times C would be defined. Notice, nowhere do you see AB equal to BA. That's because usually AB is not BA. We saw that when we had the example where A was a 2 by 3 and B a 3 by 2. One way we got a 2 by 2 matrix as the product. The other way we got a 3 by 3 matrix as the product. So most of the matrices that you will find, if you multiply them one way and then switch places, you don't get the same answer. So just be aware that usually AB is not BA. That concludes section 2.2 in Math 1114. Again, you're going to have to practice on this a little bit to try to get the hang of it. Good luck.